Okay, so this is part 2, section 3.1. It actually, so this, so I might go over 15 minutes because I want to finish up to a certain point, and then that's all that, so we're not, I thought I could finish 3.1 in one video, but I don't want to rush because these are some important concepts. So in fact, we're going to do 3.1 Wednesday and on Friday. You'll work on the second half. I'll post the video possibly tomorrow for the second half on the problems you'll be working on Friday. Okay, so let's get started on the second part. So again, we're continuing with some linear algebra knowledge. If you want, you can stop the video and write this down and then play it. I did this to save time, of course, and you can do that for future videos. Just make sure, if possible, you may want to leave some space if you do write it down, because I might make little notes, or you might want to jot down some notes when I'm going over it. Okay, and so the first definition 1, is the number of dependent variables is called the dimension of a system. All right, and so if we have the system we were talking about, this system here, since we have 2 dependent variables, then that is a 2-dimensional system, or planar if it's 2-dimensional. And the product of A times our vector Y, so if you have, this is the constant coefficient matrix, and this is our column vector, which has our dependent variables, and it equals AX plus BY over CX plus DY. And I want to go actually to this slide, so because I want to show you how, for those of you who haven't had linear algebra, or if you have and need a brush up on multiplying a matrix times a column vector, and then we may have to get into matrices times matrices, but for now it's just a matrix times a column vector. The thing to remember is, in general, for any type of matrix, you can only multiply the product if, so notice this is a 2 by 2 matrix and this is a 2 by 1, right? These two have to be the same, otherwise you are not able to do matrix multiplication or do the product of a matrix times a column vector. Okay, so those two have to match up, and the resulting vectors gives you what your final vector will be. So this tells us our final vector will be a 2 by 1, so 2 rows and 1 column. This will be a 2 by 1 vector. Okay, and how we multiply or take the product of a matrix times a column vector is we take the first row and multiply it by the first column, and that gives us the input here, which will be our first row and first column, and you don't have to circle that. And you do it pairwise, you multiply pairwise. And so what I mean by that is that, and I'll probably go back and erase this in the notes, but what I mean by that is, once you know which column you're looking at and which row you're looking at and which column you're looking at, you take this entry here and multiply it by 2, and take this entry here and multiply it by 1, and you add up their sums. So how that's going to look is, we'll get inside here for our first row, it's going to be 1 times 2 plus -3 times a -1. And actually, I should erase all that. Hold on, because I don't want all that distracted. Okay, so it's going to be 1 times 2 plus a -3 times a -1. And then the same here, so this is going to be, so this second row, we're going to multiply it again by this first column, and this entry is actually the second row, first column, right? So when we do that, we're going to get 2 times 2 plus 4 times -1. All right, make sure you go back over the video if you need to hear that again. And so our final answer then, when we look, we can simplify that, of course. Well, 1 times 2 is 2, so 2 plus 3, so that's going to give us 5. And then 2 times 2 is 4, plus 4 times -1, so that's 4 minus 4, so is that 0? Okay, so hopefully that made sense. Now let's go back and look further at the notation over here. Okay, and so again, y of t, so that's a vector, and I might stop just because it can get too cumbersome to keep writing the arrows, but just know in this chapter we're talking about vectors, so just keep that in mind. So y of t So that vector corresponds to the column vector here with our dependent variables. And so therefore dy over dt is going to be the column vector with dx over dt and dy over dt. So therefore, thus dx, the column vector dx over dt and dy over dt equals ax plus by and cx plus dy, which if we remove that out, we have our matrix A here and our column vector y. Okay, and this can extend to any number of dependent variables. For the most part, we're just going to focus on 2 by 2 matrices, but this extends to any number of dependent variables. Okay, all right, so now let's bring back our equilibrium points that we constantly discuss and talk about. And so for vectors, the equilibrium points are the points, and if we have, say, y sub naught is equal to x sub naught, y sub naught, such that a times y sub naught equals 0, 0, and we call this the zero vector. And again, if you were in, so this is the zero vector, if you were in, let's say, a 3 by 3 space, the zero vector would be 0, 0, 0. So it depends on what dimension you're in, and so this is a zero vector for a 2-dimensional space. Okay, and so therefore A, B, C, D. So if we take the coefficient matrix and constant coefficient matrix and multiply that by x sub 0, y sub 0, and set it equal to 0, 0, then that will give us our equilibrium points. Okay, if we solve this right here, that'll give us our equilibrium points. In other words, and I'm going to shorten other words, IOW, we have this systems of equations here, right? Now clearly we see that x sub 0, when both x sub 0 and y sub 0 are equal to 0, 0, that we have a equilibrium point. And we call that the trivial solution. So I've been saying it, but now we have the formal, so that's actually called the trivial solution. Well, how do we find the non-trivial solutions? Okay, and so the trivial solution, every linear system has the trivial solution. Okay, to find the other equilibrium points, well, let's assume, so if we look back at this first equation here, let's assume A is not 0. Okay, well, if A is not 0, then we can divide by it and we can solve for x sub 0, and x sub 0 equals negative b over a times y sub 0. Okay, feel free to go back on the last slide to verify that equation. Now, okay, and so you can check that and verify that. Now, to continue with that, so now we're going to take this x sub 0 and plug it into the second equation here, because there's an x sub 0 there, right? And so, and that's where this equation comes from. So c times the quantity x sub 0, which is negative b over a times y sub 0, plus d times y sub 0 equals 0. This should look familiar from chapter 2, right? When we were looking for our equilibrium points, how we factored out. So we factor out a y sub 0, and we're left with this inside here, and you can verify that, and that equals 0. So that tells us that y sub 0 equals 0, or negative b times c over a plus d equals 0. Okay, and if we just pretty that up a bit, we'll get a times d minus b times c equals 0. And some of you who've had linear algebra should notice that that looks familiar, especially for a 2 by 2 matrix, which we'll talk about on the next slide. But what this tells us that we have a non-trivial solution if and only if, in fact, AD minus BC equals 0. Okay? So this leads to definition 3, which is the determinant of a 2 by 2 matrix A is AD minus BC. And here's the notation for determinant of A. That represents determinant of A. And so a theorem says if matrix A, so this is a matrix A, with determinant A not equal to 0, then that tells us the only equilibrium point for this equation here is the origin, or is the point 0, 0. That's the only equilibrium point. Okay, and just to follow up, so in terms of thinking about that, in terms of notes, then just some more terminology, we say that a matrix is singular or degenerate if the determinant equals 0. So if it equals 0, we call that singular or degenerate. We say it's non-degenerate if the determinant of A does not equal 0. Okay, And when the determinant of A equals 0, you will have non-trivial solutions, right? Because again, the determinant of A is the AD minus BC, which we just proved on this last slide that we'll have non-trivial solutions when AD minus BC equals 0. Okay? Hope that made sense. Now, this is sort of the last thing I'm going to do for this part. Actually, I have something else for you to do, but this is sort of the last main principle, the last main new thing that I want to talk about. So hopefully you're following along up to this point and you're okay with everything. So we have what we call the linearity principle or the principle of superposition. And this says, suppose dy over dt equals a times y is a linear system. Suppose this is a linear system. And this is to actually show that it's a linear system, okay? Or some characteristics, I should say. So if y of t is the solution of this system and k is any constant, then k times that y of t is also a solution. And we had something similar to that in earlier sections, I think around chapters 1.8 and 1.9 when we talked about those solutions there. So you can sort of refer back to your notes, and that's for the exam anyway, so you're going to have to look back over that. Now, if y1, so that's the first principle, if you can show that y of t is a solution, then any constant times that y of t is a solution. But also, if you have two solutions, y sub 1 of t and y sub 2 of t, if they're two solutions, then if you add them together, y sub 1 of t plus y sub 2 of t is also a solution, okay? So you could just put them together. Now, 3 is basically putting 1 and 2 together. So that's why I made this little note down here. If we put 1 and 2 together, then we can say that if we know 1 and 2 exist, then we can say, well, if we know y of t is a solution, then we know, so 1 is telling us if y of t is a solution, then k times y of t is a solution. And 2 is saying if we have two different solutions to the system, then we can add them together, and that also gives us a solution. Now, 3 is bringing it home by saying, well, if we can put them together, then we can put them together and throw some constants in front of them, and that'll also be a solution, okay? And so this is called, when you do that and put constants with them, we call that a linear combination of y1 and y2. Okay, I hope that makes sense. I know for those who took linear algebra, this is sounding familiar. If not, it still should make sense. So if not, just go back over this. And so here we have this example of the linearity principle, which I'm going to go over the example in 1 minute, but I just want to say this because I'm going to, you're actually going to have a homework assignment. So before I do this, okay, I want to say that the next slides about proving the linearity principle, this is in your, I want you to see your book and write down in your book, because I think they do a really good job. Sometimes they condense a lot of things, but I think they do a really good job of showing how to prove it in general for any 2x2 matrix. And so I want you to write down how they prove those two, principles, and make sure you have that in your notes. And also so I'm not done with the video yet. But I want to state this sort of midway and not at the end. The homework problem. So for Wednesday's class, you will be assigned groups. So I will be assigning groups. But these are the homework problems. So up until after I show you an example with the linearity principle, you should be able on Wednesday in class to solve these problems. So it's 2, 5 through 6, 8, 14, 30, plus the problem on the last slide, okay? And you're going to be working with groups. Now, this is not the time to come into class, and when you get in your groups, get on your phones, text, and all this. No, this is the time you want to maximize your time, especially if you haven't been doing well on your homework or in the class. You want to make sure this is your time. When we flip the class, this is your chance to strengthen your homework scores and hopefully strengthen your quizzes and your exam for next week. So you want to come in, I'm going to put you guys in groups, and you're just going to start working on these problems. Like I'm not saying anything. If you have any questions, I can come work with your groups individually. Make sure you bring your notes with you, because I'm not answering questions unless you take notes, but make sure you bring your notes with you. And then you can get possibly these homework problems done by the class time, because they're not too bad. I didn't want to give you all the problems from this section. That's why I'm breaking up this section into two, to Wednesday and Friday's class. Okay, so just keep that in mind. All right, so the last thing, let's talk about this. So the linearity principle. All right, so we talked about the principle, those two main conditions, and then 3 is sort of a byproduct of those two conditions. All right, so let's look at this example. So let's say dy over dt equals, we have the matrix here A, which is our constant coefficient matrix, and then times y. And I'm dropping off the arrows, but these are still representing vectors. I just didn't want to confuse you with all the arrows. Now let's say you're given these two, and you're told they are solutions to this dE, to this linear system. Then that means, since they're two solutions to that system, any constants I throw with them should also be a solution. And so let's say, assume that k sub 1 is -2 and k sub 2 is 3, and then y sub 3 of t, which is equal to -2 times y1 of t plus 3 times y2 of t, it should also be a solution. And remember, to check if it's a solution, you have to show, what you're doing is you have to show that the left-hand side, which is the derivative of y sub 3, with respect to t, is equal to the right-hand side, which is the constant coefficient matrix A times y sub 3. Okay, I'm going to do an example because this is actually, add this onto your homework problem. This one I'm actually collecting. I'm collecting this on Wednesday, so you probably want to start with this problem first when you get in your groups, or if you want to do it before then. But I'm collecting this one on Wednesday. I'm going to give you an example now of something somewhat similar so you can see the process, especially if you've not had linear algebra. Then there's some things that you need to know in order to do this problem. Okay, so we're going to now, so these other notes that I put on the slides, that's going to be part 2. That's going to be what we work on Friday's class. But on Wednesday's class, this is all I want you to focus on. Okay, so let's say now, so I'm actually using the same dE and assuming that y1 and y2, those were given as solutions. But this time, instead of showing whatever I gave you for the homework, we're going to show that y3, we're going to let y3 equal y sub 1 of t minus 2 y sub 2 of t. So in other words, what this is saying here is that k, in this example, k sub 1 is 1 and k sub 2 is -2. Okay, so that means that should also be a solution, because any constants you tack on there, if you know two of your solutions, any constants you tack onto those functions should also be a solution when you put them together as a linear combination. Okay, so we need to show that dy sub 3 equals the constant coefficient matrix A times y sub 3. Okay, well, y sub 3, again, it equals, here's y sub 3 here. Now putting this in column vector form, y sub 3 equals, well, y sub 1 is given here, right? So that's how we got this first column vector. And then -2 times y sub 2, which is given here. And y sub 3 equals e to the 2t. So nothing changes here, right? Because the coefficient is 1. But this 2, so for those, if this is new to you, when there's a constant outside your vector, okay, your column vector, you multiply that to each term. And if you have more terms, you would multiply that constant to each term inside that vector, okay? So then that will look like what we have here. So, and if you, I mean, you could distribute that sign, but I didn't. I just kept that minus on the outside. Okay, and so that's how we got -2e to the -4t, and then 4e to the -4t. Okay, so I hope that made sense. And now putting it together, and so here's what's going on when you're adding. So if you had, let's say AB, let's see, minus, let's say CD, right? Then that equals A minus C and B minus D. All right, so over here we subtract these two, and since the exponents are different, we can't bring them together, and then we subtract these two. Okay, and that's how I got e to the 2t plus 2e to the -4t, and then -4e to the -4t. Okay, And now we have to take the derivative, because remember what we're trying to do. We're trying to show that the left-hand side equals the right-hand side. Okay, and we're going to do this, so we're not going to do the question marks like we've been doing before, but instead we're going to take the left-hand side and simplify that through, and then take the right-hand side and simplify that through, and show that they're equal. Okay, and so if you take, now this is some Calc 2 review, if you, Calc 1 actually, if you take the derivative of each of our entries, then the derivative of the top using chain rule, that first entry, that's going to be 2e to the 2t minus 8e to the negative 4t. Hopefully you guys remember that. And then the derivative here is going to be a positive 16e to the negative 4t. So this right here is our left-hand side. So now, to show that it's a solution, to show y sub 3 is a solution, we have to show that the right-hand side is also equal to the left-hand side. Well, the right-hand side is given here, right? So we have our constant coefficient matrix times y sub 3, and we found y sub 3 here, right? So remember, so be careful, it's times y sub 3. Okay, and so, and we're almost done. And so we take the constant coefficient. This is still a 2 by 1, although it looks like it's more complicated. This is still a 2 by 1 matrix, and this is a 2 by 2 matrix. So again, we do this row times this. It's just one column. And then we're going to take that row and times this to get our answer. So if we take this first row and multiply it through, then this is going to be 2 times that entire first entry, and then plus 3 times that entry. And that's how we get this line right here. Okay, so it's 2 times the quantity e to the 2t plus 2e to the negative 4t plus 3 times negative 4e to the negative 4t. Okay, and then we do the same for this second row, first column again. So that 0, that's just going to go away. So that's completely just 0, right? And then right here it's going to be positive 16e to the negative 4t. Okay, and then from there you just simplify the top using some algebra, and the bottom is already simplified, and we just show that the left-hand side and the right-hand side are equal. So therefore y sub 3 is also a solution to that differential equation model. Okay, so we are done. I hope it all makes sense, and I will see you all on Wednesday.